Welcome to a code report solution video. In this video, we're going to be going over the solution to problem 2 from HackerRank 101 Hack 53 entitled Cut Board. The problem states a rectangular board of size n by m has 1 by 1 cells, x consecutive cells from the first row starting from the top left and y consecutive cells from the last row starting from the bottom right are cut off. And the question asks, can you fill all the cells of the remaining board using some dominoes such that none overlap or hang off the edge? Complete the function fill board and print whether the remaining board can be filled with dominoes, and if yes, print one way to place the dominoes. And note that our board at minimum is going to have 3 columns and 3 rows, and our x and y is going to be between 1 and m. So we're only ever going to have sort of deleted cells from our top and bottom row because x and y can't exceed m, which is the length of our row. So let's take a look at the example that HackerRank provided. So in this example, n equals 3, the number of rows, m equals 4, the number of columns, and x and y equal 1 and 3. So you can see here, originally we had a 3 by 4 board, but then we delete 1 cell from our top row starting from the top left, and then 3 cells starting from our bottom row and the bottom right. And that leaves us with this board, and the question asks, can we fill this board up with dominoes, which is a 2 by 1 tile? And if so, print out yes and a possible configuration of that board. So our output is simply going to be the x and y coordinates for each one of the dominoes on a single line. So each domino will have its own line. And so you can see here that we're able to do this with 5 different dominoes. And so at first glance, sort of my intuition for this algorithm was that we just we're going to loop through sort of backwards and forwards. So we're going to have 2 different states. In state 0, we're going to loop from left to right, and then every row we're going to switch a state. So once we've looped from left to right, we're going to come down and loop from right to left, and then we're just going to store the coordinates of each of these and then print them at the end. And so just by looking at this example, it looks like that works. But if we look at a different example, we can see that we're going to run into problems. So in this example, we have n equals 4, m equals 5, so 4 rows and 5 columns, and then 4 cells deleted from both the top and the bottom row. And we can see here that if we use that algorithm, it's going to fail. So at first, we're going to put a domino here, and then we're going to start looping from right to left. So we'll put a domino in these 2 cells, another domino here, and you can start to see the problem. So at this point, we're gonna try to put a domino in these 2 cells, and depending on your implementation, you'll either end up returning no because you don't think it's solvable because you've hit a deleted square, or you're going to output the wrong coordinates. And this board, of course, does have a valid solution that looks like this, but that's not going to be achievable by just switching states back and forth. So there's one sort of modification we need to make to this algorithm, and that's basically checking that at the time that we finish a row, if we're not in the midst of trying to complete a domino, meaning that we're going to have a vector storing the 4 coordinates for our domino, so xy for this piece of the domino and xy for this piece of the domino. So if we have our vector equal, the size of our vector equal to 2, we know that we have a domino that's placed vertically. So at that point, we know we need to continue switching states. So if we're going left to right here, we're going to have to go from right to left here. But if we don't have a domino half completed, we can start either from the left side and start looping left to right, or start from the right side and start looping right to left. And that's going to be informed by basically how many rows we are away from the last row. So we always want to loop from left to right if we are basically 1 row away, or sorry, 2 rows away from the last row, and we always want to loop from right to left if we're 1 row away. So basically, once we've finished this row, we know that because in this row we're 1 row away from the final row, we want to start looping from right to left in case we have this extra piece here. So we'll know that if it's possible, we're going to end up filling this domino in this way. And one thing to note that I didn't mention at the beginning is just that we are going to do a check at the very top to make sure that the number of tiles that are left in our board once we've deleted our X and Y cells is even. And if we know it's not even, then it's definitely not going to be possible. So let's take a look at the code. So this is a relatively large function compared to some of the other examples or problems that I've covered. So we're going to sort of delete some of this stuff and focus on the main part of the function. So at the top here, you can see the case that I just mentioned. We're checking to see that if the size of our board, once we remove the X and Y tiles, isn't even, then we're going to set solvable to false. So we're not going to come in here. If we do come in here, we're going to do some initialization. So V is going to be for the coordinates of each domino. Res is going to be what we're going to output at the end, which is going to contain all of the different coordinates for each of the dominoes. So it's a 2D vector. Our state and our count. So the count is just going to be the number of tiles that we've traversed over, and the state is going to be whether we're looping from left to right or right to left. So we're going to hide this stuff, and then at the end we just have our output. So we're outputting no if it's not solvable, and we're going to output yes, the number of tiles or dominoes. So that's just going to be this number. So our board with X and Y removed divided by 2, and then we're just going to output our board. So I'm going to hide sort of the beginning and the end, and we're going to focus on this middle part. So you can see here what we're doing is this is a 2D vector, li for loop info, which is just going to be a way to sort of save space, and we don't need to write two explicit for loops when we're looping left to right or right to left. So the first element of each one of these states, so this is state 0, this is state 1, you're looping from 0 to m, and you're incrementing our index by ++1. And when we're looping from right to left, we're starting from m-1, and we're going to 0, and we're doing -1. So the way our inner loop is it's not equals. So as soon as you hit m, or as soon as you hit -1 for the corresponding directions, you're gonna end the loop. And then for this inner loop, we're just referencing, you know, state 0, state 1, state 2, and that gives us the ability to just have one loop. So once we have this, all this inner loop is doing, we'll come back to this little special case, is basically if we're in the part of our board that hasn't been deleted, so if our our count of the number of elements or tiles we've traversed is greater than or equal to x or less than n times m minus y, we are going to sort of save the coordinates. So we're going to push back into v, which is our vector for our domino coordinates, i+1, because we're looping 0 index, but we want to output 1 index, so we need to add 1 here. And then every time our v, which is the coordinates storing the coordinates of our current domino, equals 4, we push that to our result, and then we clear it. And then inside this loop, we make sure we're doing a post increment on our count, so we know when we need to do this operation based on C. This line here is for that if at any point we end up in our last row, which is I equal to n-1, and our column index is greater than basically where we started deleting our Y tiles, we know that it's not solvable. So we set solvable to false. And that combined with this sort of special case. So what we're doing here is we're saying if the size of our vector is equal to 0 and we're not in our first row, because we know we always want to loop from left to right given that we're in our first row, you can set your state optimally based on how far away you are from the last row. So because we haven't incremented I yet, we want to check that this is even, not odd. And that brings us back to our case where we said, you know, if our next row that we're going to be iterating is 1 away from the last row, we know that our current row is going to be an even number of rows away from it. So whenever this is even, we're going to set set s equal to 1, and whenever it's odd, we're going to set s equal to 0. And in all the other cases, we know that we're in the middle of finding the coordinates for a domino. So v.size, we could assert in this else case, is always going to be equal to 2. And in that case, we just need to switch states. So if we're looping from left to right, we know we need to loop now from right to left in order to complete that domino, vice versa. So using this code, you'll be able to solve this problem. So this is the whole solution again, and the complexity of this solution is either linear in the number of tiles or quadratic in the number of columns times the number of rows. So big O of n times n. As always, if you enjoyed this video, hit that like button. Make sure to follow me on Twitter for reminders 30 minutes before contests start. You can find all of the code that I use in my videos on my GitHub page. All of the links are in the description down below. And finally, if you want to make sure you don't miss any of my upcoming videos, make sure to hit that subscribe button. Thanks for watching, and I'll see you in the next video.